Okay, so right here's the answers to the card sort. If you guys want to pause the video and check on that. The first number, that represents the factored form of the equation. The second one is the graph. That's the capital letter. The lowercase letter is the description about the degree, leading coefficient, number of zeros, absolute max, absolute min. And then the last one, the Roman numeral, tells about increasing, decreasing, relative max, relative min, concave up, concave down. So you can pause this, check on that if you have finished up with that already. Okay, so we got two type lessons we have to do today. The first one, it says the goal for this lesson is to find a quick way to expand polynomials of higher degree. Let's start by looking at a binomial that is raised to different powers. So here I've got a binomial, two terms, in parentheses. If I raise that to the 0 power, okay, well, anything raised to the 0 power is 1. So what they want you to notice here is when I raise something to the 0 power, my final answer has one term. All right, then if I had u plus v to the first, that's just 1u plus 1v, that has two terms. And we follow that through. This is 3 terms, 4, 5, and 6. All right, so answer the following questions about patterns in the expansion. So why is multiplying out u plus v raised to the nth a binomial expansion? And again, the key there is the word binomial. Binomial means two terms. And what we have in parentheses is two terms. So anytime we have two terms being added, raised to a power, that's when we have a binomial expansion. So one key thing here is we're going to focus only on addition today. If they're being added, we might look at subtraction later. Again, I haven't looked ahead. Excuse me. But you've got a few extra steps you have to do if you go with subtraction. B, what term does each binomial expansion begin with? So if you look at each one of these, what do they begin with? 1u to the first, 1u to the second, 1u to the third, to the fourth, to the fifth. So each term begins with 1 times u raised to whatever power we're being raised to. So this is 1u, and it's raised to the same power that the binomial is raised to. Same power as binomial. Okay, what about the last term? It's 1v, and it's also the same power. Again, if you want to check, just look at the last terms. Now, what happens to the powers of u as you read from left to right? They decrease by 1. Right, u to the fifth, u to the fourth, u to the third, u to the second, u to the first, u to the 0. Right? U's decrease by 1. What happens to the powers of v as we read from left to right? They increase by 1. And then E, how many terms do you have in an expansion raised to the power of n? So again, what they're looking at here, if this was u to the fifth, we had 6 terms. U to the third, we had 4 terms. U to the second was 3 terms. So if I raise something to the power of n, how many terms does that give me? 1 more than n. So there'd be n plus 1 terms. So this binomial expansion fits into what's called Pascal's triangle. It's a name for a French mathematician. So if you want to see if you can figure out the pattern, if you've never seen Pascal's triangle before, you might want to pause the video and see if you can do that. But here is how it works. So Pascal's triangle, you always start it with 1 and then 1, 1. So it always starts 1, 1, 1. Now the next row, we bring the 1 down. We combine these terms to get a 2, and then there's a 1 at the end. All right, and then this pattern just continues. So I bring the 1 out front, combine 1 and 2 to get 3. 2 plus 1 is also 3, and then 1 at the end. All right, so we just add the middle terms over and over and over. So again, if you want to look here, 1 plus 5 gives 6, 5 and 10 give 15, 10 and 10 gives 20, 10 and 5 gives 15, 5 and 1 gives 6, and then bring the 1 out front. So if I had to complete row 7, there's a 1 out front. 1 and 6 gives 7, 6 and 15 gives 21, 15 and 20 is 35, 20 and 15 is 35, 21, 7, 1. And then for the 8th row, again, bring the 1 down. 1 and 7 is 8, 28, 56, 70, 56, 28, 8, and then the 1 on the end. So hopefully you see the pattern. If I raise something to the 0 power, I just got the constant. If I raise something to the 3rd power, you're going to have to the 3rd, so 1x to the 3rd, 3x to the 2nd, 3x to the 1st, plus 1 as a constant, right? If it was just x plus 1 in there. So here, if I'm looking at u plus v to the 7th, I go to the 7th row. It has 1, 2, 3, 4, 5, 6, 7, 8 terms. And so instead of having to actually distribute out, because, again, think about what we're doing. U plus v to the 7th. That would be u plus v times u plus v times u plus v, and so on. So I've got 7 parentheses, and I'd have to distribute each time. Just think about how much time that would take. A lot. So what we're going to do instead is we're going to use Pascal's triangle because it's raised to the 7th power. We're going to go to row 7, and this is going to be 1u to the 7th. Plus 7u to the 6th, v to the 1st, plus 21u to the 5th, v to the 2nd, plus 35u to the 4th, v to the 3rd, plus 35u to the 3rd, v to the 4th, plus 21 u to the 2nd, v to the 6th, v to the 5th, plus 7u v to the 6th, plus 1 is my constant. So hopefully you see where this comes from. Pascal's triangle just gives the coefficients. And then I know it's going to be u and v. U keeps decreasing its power by 1. V keeps increasing its power by 1. And I just realized I didn't write v to the 7th here at the end. Right, v needs to go up another power. Because it tells me to write the binomial expansion for u plus v to the 8th. So again, I would use Pascal's triangle, which is on the previous page. Because I'm on row 8, see, and I didn't write this down. Isn't that great? I'm just going to write the coefficients, which are 1, 8, 28, 56. My numbers are too big. 1, 8, 28, 56, 70, 56, 28, 8, and 1. All of them have pluses between them. And then u's, the power starts at the top and they decrease by 1. So u to the 7th, u to the 6th, u to the 5th, u to the 4th, u to the 3rd, u to the 2nd, u to the 1st, and then u to the 0. And then I've got v to the 0, v to the 1st, v to the 2nd, v to the 3rd, v to the 4th, v to the 5th, v to the 6th, v to the 7th, and v to the 8th. So hopefully you can see here how on number 1, if I had x plus y to the 6th. So again, I look at the 6th row. The coefficients are 1, 6, 15, 20, 15, 6, and 1. I'm going to have x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. I'm going to have y to the 0, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, y to the 6th, and then plus signs between them all. So you can see I kind of ran out of space. Hopefully it's a little bit easier for you guys on paper. But the last one's kind of interesting. I didn't know this last one. This is new to me. Notice how the coefficient here has a 2 in front of it. We can still use Pascal's triangle. So here's the way that would look. For the 3rd row, that's going to be 1, 3, 3, 1. And then I'm going to start with x to the 3rd, x to the 2nd, x to the 1st, x to the 0. And then I'm going to have 2y to the 0. Plus 2y to the 1st. Plus 2y to the 2nd. Plus, and then here at the end, this one's going to be 2y to the 3rd. And then we have to simplify this. So 2y to the 0 is 1. So that just leaves me with 1x to the 3rd. And then 3 times 2y to the 1st is just 2y. So 2 times 3 is 6. So that's 6x squared y. Next, 2y to the 2nd, that's 4y squared. And then 3 times 4 is 12. X to the 1st, y to the 2nd. And then, look, I put the cubed in the wrong spot here, didn't I? It should be 2y all cubed, not just y cubed. So this would be 2y cubed, which should give me 8y cubed. Once I've cubed it. Okay, so right at the very top, this is important for all the next 4 problems, is we know ahead of time that all of these are the result of a binomial expansion. So because we know that, we can do the steps that we're going to do. If we didn't know it was a binomial expansion, it wouldn't be this easy. We want to use the patterns in binomial expansion to find the binomial that is raised to a power and write the equivalent form. Use the binomial form to find the number of solutions and determine if each solution is complex or real. Use a graphing calculator to check your answers. So I didn't bring a graphing calculator with me, but we'll talk about how you can do that. I'll probably have to use Desmos. Okay, so when I look at this, I know it's a binomial expansion, and so the first thing I can look is how many terms is this expansion? It is 5 terms total, which means I know that it is a degree 4 binomial expansion. So I know it's going to be something raised to the 4th power because there are 5 terms. Now, the next thing we can do is look at the signs. This sign is positive, negative, positive, negative, positive. So the signs keep alternating. So I know between my 2 terms, I'm going to have a subtraction sign because I have alternating signs. If they were all positive, it would be positive between them. But because it alternates, it's going to be a negative. Okay, then let's think about the first term here is x to the 4th. So what would need to go in here so that way when I raise it to the 4th power, I get x to the 4th. So really I'm taking a 4th root of x to the 4th, and that's 4. And then if you think about the v term, the last term, this must be v to the 4th. So what raised to the 4th power gives me 16? That would have to be 2. So you could take a 4th root of the constant, 4th root of 16. So this here would be my binomial expansion. So when it says check using a graphing calculator, what they want you to do is type in line 1 y equals, and then type in this entire polynomial. And then in the second line, type y equals x minus 2 to the 4th, graph them both, and see if they're the same thing. And they would be. Okay, so again, if you graph that, you could see they're the same polynomial. One is in factored form, and one is in standard form. It says a way we can check our work here is rewrite this using Pascal's triangle to see what we would get. So because it's a 4th term, that would be 1, 4. So again, you could either go back and look at your Pascal's triangle. 1, 3, 3, 1. It's going to be 1, 4, 6, 4, 1. So I'm going to have 1, 4, 6, 4, 1. I'm going to be alternating the signs. So I've got a positive and then a negative, and then a positive, and then a negative, and then a positive. But that's what you have to do when this is a subtraction sign between them. We alternate the signs. And this would start as being x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, x to the 0. And then we would have 2y to the 0, which is just 1. 2y to the 1st, 2y to the 2nd, 2y to the 3rd, and lastly 2y. I'm putting my, there we go, 2y to the 3rd, and 2y to the 4th. Then simplify these. This here, negative 4 x cubed 2y, that would be negative 8x cubed y. This one, 2y squared, would give 4y squared, which leaves positive 24x squared y squared. Here, 2y to the 3rd, that's going to be 8y cubed. 8 times negative 4 is negative 32xy cubed. And then the last one, 2y to the 4th, is positive 16y to the 4th. I messed up that whole thing. Doggone it. Look, why am I putting y's? There's no y here. I just got a bad habit now because we did the y's before. So there should be no y, no y, no y, and no y. Hopefully you can see that's all the correct work. I just added a y for whatever reason. So negative 8x cubed plus 24x squared minus 32x plus 16. And then don't forget, we can bring down the 1x to the fourth that was at the beginning. So we have verified by checking the graphs. We rewrote Pascal's triangle to verify. They're the same. Last thing it asked me to do is determine the number of solutions and determine if the solution is complex or real. So if I were to graph this, it's going to have one x-intercept. That x-intercept is going to be at 2. And how many times does that x-intercept occur? It occurs 4 times. So again, it has an even multiplicity, so that means we know it's going to bounce off. And again, it almost looks like a parabola, but it's very flat at the vertex. So where an x to the second parabola would look something like this, and x to the fourth, it comes in here, but it gets like very flat like this. And then where x to the sixth is even flatter across there. Okay, that's kind of how as we raise them, they just get flatter. They're not flat like this. This is an over-exaggeration, right? But they appear much flatter than a regular x to the second. So working all of these out is the same way. And for myself, I'm going to try to save myself some time. You guys try to work each one of these with the time you got left in class. See if you can do them. And then I'm going to put the answers up at the end. Here's the answer to 2. Notice about the x-intercept. It has one solution at x equals -3, and its multiplicity is 5. So again, it almost looks like a cubic. It's going to snake through. Another thing I wanted you to notice here, because every term was positive, we had a plus in parentheses. Here's the third one. Once we graphed it and looked for the roots, the solutions, well, because my parentheses in factored form was x squared plus 1, if I solve that, I get imaginary numbers. So all 4 solutions are complex. Also, the big trick here is notice how the x values, they are no longer going down by 1. X to the 8th, to the 6th, to the 4th, to the 2nd, and then x to the 0. We're going down 2 each time, which means, again, all you got to do is think about, because there are 5 terms, this has to be a degree 4 in parentheses, or a 4th power out here. And so x to the 8th, if you took a 4th root of that, it would leave me with x to the 2nd at the beginning. And that gives you that decreasing power by 2. If it was decreasing by 3 every time, then it would be an x cubed up there. If it's decreasing by 4, the powers are decreasing by 4 every time, it'd be an x to the 4th, and so on. So the last one here is pretty much the same as number 3, except they have alternating signs this time. So because they're alternating signs, this is a negative inside the parentheses. Well, because this is a negative, when I solve it, I don't get imaginary numbers anymore. I will get x equals plus or minus 1, and I will get that answer 2 times. I don't think this answer's right. I think both these should be multiplicities of 4. Nope, I'm wrong. Okay, so let's work out the end. So if I've got x squared minus 1 equals 0, each one of these roots is going to happen 4 times. So that leaves me with x squared equals 1. So x equals plus or minus 1. Yeah. They're wrong. These each have a multiplicity of 4, not 2. That has to be.